Hi everybody, we're going to lead into this wonderful world of functions, which is a huge topic in all of mathematics, one of the most important topics we talk about. The book does it in kind of a goofy way, and we don't have a lot of time this year, so I'm going to run through this little packet from this website, eMath Instruction. If you notice up here in the top corner, there is a little QR code, and if you point your phone's camera at that QR code, it will lead you through a nice probably 20-25 minute video of how to go through all of these problems. I'm not going to do that. I'm going to run through this in about 10 or 12 minutes. So if you want to go slower, you can do that along with the guy who created these worksheets. So we're going to talk today about an introduction to this idea of functions, which again is a huge concept in mathematics. A function is defined for us. A function is a clearly defined rule that converts an input to exactly one output. And that's the idea here, the big thing. Every input has exactly one output. If an input has more than one output, it's not a function. These rules often come in the form of equations, or graphs, or tables, or verbal descriptions. So we're going to discuss just an introduction today to functions. So here's our exercise number 1. It says, consider this function rule. So here's our rule. We're going to take the input and multiply it by 2, and then we're going to subtract 1, and that will give us the output. Everything we've done up to this point this year has had one variable. Now we're going to step it up, and we're going to use 2 variables. Our input we're going to call x, and our output we're going to call y, and you recognize those x, y's as the numbers we use for graphs. So what we're doing is stepping up our game now. Instead of just being in the number line with one variable, we're going to use the coordinate plane with 2 variables. All right, so our input here is our output rather. We're going to take the input, multiply it by 2, and then subtract 1 to get the output. So if our input is 0, I multiply that number by 2, and then I subtract 1 to get the output. My output would be -1. If my input is 1, I take that input, I multiply it by 2, and I subtract 1. 2 times 1 is 2, minus 1 would be +1. If the input was 2, 2 times 2 is 4, minus 1, the output would be 3. If the input was 3, 2 times 3 is 6, minus 1 is 5. And we see a nice little pattern there coming out for the output. So what happens with these input outputs is we get x, y coordinates. If x is 0, y is -1. If x is 1, y is 1. If x is 2, y is 3. If x is 3, y is 5. What we're going to do is I'm going to do this question C before I do question B. I'm going to graph those things. So when x is 0, we remember how we graph these. We do x before we do y. We run before we jump. So with an xy coordinate of 0, -1, I start at the origin at 0, 0. I go over 0 and down 1. So over 0, down 1 gives me a point right there. The next point is 1, 1. So I'm going to go from the origin again over 1 and up 1. And there's my new point. Next point is 2, 3. From the origin, I start again, go over 2 to the left and up 1, 2, 3 to the right. And there's my point. For 3, 5, again, I start at the origin. I go over 3 and up 5. And there's my point. The question B says, write an equation that gives this rule in symbolic form. So the question is, what is the y equal to? What is our rule? Well, the y every time is equal to 2 times the x value, take away 1. 2x minus 1, there's our rule. And very often these functions will start with a y equals. Tomorrow we're going to see slightly different notation. But y equals tells us it's a function. Question 2, or exercise 2 here says, in the function rule from above, what input would be needed to produce an output of 17? So let's see, if I needed an output of 17, I could keep going in my table and keep counting up. 3, 5, I'd go 7, 9, 11, 13, 15, 17. I could figure it out that way. I could kind of work backwards I could also use my equation here. If the output was 17, if that would mean the y is 17, the output is 17, and I get that by taking 2 times the x minus 1. Oh, there's a little equation. Now I can solve it. I could add the 1 or work backwards from that, the rule we were told up above. That would be 18, and then I would divide by 2. So our input should be 9. So let's check that out. If I take 2 times that 9 and subtract 1, I do get that 17. The question specifically asks, why is it harder to find an input when you have an output than finding an output when you have an input? Well, the input, we're going to take that input and do a bunch of stuff to it and get the output. To do the output, or if we're given the output, we have to kind of do those things in reverse to find what the input is. So it's a little more complicated. All right, question exercise 3 here says, a function rule takes an input n and converts it to an output by increasing 1/2 of the input by 10. Determine the output for this rule when the input is 50 and write the equation for the rule. Okay, I'm going to start with the equation here instead. It's going to take an input called n and converts it to an output called y. Okay, so we're going to start with a y equals again. Now in this case, the variable's not x, it's n. So it's going to take that n and increasing 1/2 of the input by 10. Well, let's see. 1/2 of that input would be 1/2 times n. And I'm going to increase that, so increase it by adding it by 10. So there's my rule. I've written the equation for the rule. The other part of the question says, determine the output for this rule when the input is 50. Well, if I input 50, I take half of that 50, which would be 25, and then I'd increase that by 10. So my answer would be 35. Okay, so we're writing a rule, and we're figuring out what the output is for that particular input. Our exercise 3 at the top of the next page, or exercise 4 rather, here's the difference between a function and a non-function. It says function rules do not always have to be numerical in nature. They simply have to return a single output for a given input. The table below gives a rule that takes an input for a neighborhood child and gives as the output the month that he or she was born. Why can we consider this rule a function? Well, our definition of function is that every input has exactly one output. Every child has exactly one birth month. So that validates our rule as a function, right? Every child was born in exactly 1 month. You can't be born in more than 1 month. Question B says, what is the output when the input is Rosie? So I'm going to look at my table. If the input is Rosie, the output is February. Question C says, find all the inputs that give an output of May. Well, let's see. We need an output of May. If I look at the table, there are 2 places that have an, or two children that have an output of May, both Nico and Zeke. The question says, why does this not violate the definition of a function, even though there are 2 answers? So here's the thing with a function. We have an input that has exactly one output. It doesn't matter that the output has more than one input. All that matters is that the input has exactly one output. May can have more than one person born in it, but each person can only be born in 1 month. So it does not violate the definition of function. Functions are useful because they can be used to model things that are happening in the real world. Every time we see a graph, when you see a COVID graph on the news, you're modeling something that's happening, a real world model. And we use that coordinate plane. Very often, our x-axis is time, because at any given time, something's happened. Exactly one thing is happening. So our exercise 5 here says, Charlene heads out to school by foot on a fine spring day. Her distance from school in blocks is given as a function of time, of the time in minutes that she's been traveling from school. The function is represented by this graph. So we've seen graphs as a verbal, or we've seen functions as a verbal description. We've seen them as a table. We've seen them, we're seeing them now as a graph. And you should be able to, at this point, to read a graph pretty well. Question here says, how far does Charlene start off from school? When she starts off at school, her time would be 0. And I look up and I can determine, I should determine first of all, what's happening on this graph. The x is time, the y is her distance from school in blocks. And I notice that 10 is here and 20 here. I should figure out what we're counting by. And I think 2, 4, 6, 8, I think we're counting by 2s. So how far off does Charlene start from school? She's 22 blocks away from school. What's her distance from school after she's been walking 4 minutes? Well, let's see. I notice here the axes are given different scales. The x-axis is counting by 1s and the y-axis is counting by 2s, so we're careful there. After 1, 2, 3, 4 minutes, if I look up, I'm at 10, 14, so it looks like she's 14 blocks away from school after 4 minutes. After walking for 6 minutes, Charlene stops to look for her subway pass. How long does she stop for? So this is really important to look at the graph, the part of the graph that indicates where she stopped, where her distance isn't changing. Notice that didn't drop down here, right? Her distance away from school isn't changing at all. It remains horizontal. We can tell how long she's stopped by looking at how many minutes we're flat for. Charlene then walks to a subway station before heading to school. How many blocks did she walk to the subway station? So let's see, she's going from here to here. She walked 2 blocks. How long did it take her to get to the school once she got on the train? Then I'm looking back at the minutes. She went from 11 minutes to 15 minutes, so I think 4 minutes there. So functions, we should be able to read graphs and interpret what's going on. I want you to try the homework problems on the next couple of pages. Come back with questions next week. Okay, circle ones you don't understand. Come back with questions next week. And let me just briefly walk you through the instructions here. First part says decide whether each of the following relations is a function. Go back to that definition of functions. Okay, does each input have exactly one output? Question 2 is asking in each of the following examples, use the input-output chart to decide if it's a function. So that's for question A and question B. For C and D, there's no calculation to be, actually for B, C, and D, there's no calculation to be done. For C, you're just going to look at the graph. For D, you're also just going to look at the graph. And the question is it a function? Yes or no? Does each input have exactly one output? And then I think questions 3 and 4 are pretty straightforward. In 3, you're interpreting a graph, and in 4, you're going to draw a graph. Okay, so again, come back on Monday with questions for me. And that's it, guys. Have a great Thursday. I guess it's Thursday. I don't know. Bye-bye.